SwayamPrabha. Digital India. Educated India.
In this lecture, we'll be discussing the concept of phase margin and gain margin and how these are important parameters for designing control algorithm in frequency domain. So the topic is control design. Let me write some notes, then we'll start the phase margin and gain margin in the frequency domain and how we can find from the magnitude and phase plot. Control system or control design in the frequency domain involves analyzing and designing control system based on their frequency response. Two key important concepts that play a crucial role in frequency response or in frequency domain. Analysis and design are phase margin and gain margin. Let's start with the phase margin and how we can come up with the phase margin from the frequency response. Phase margin. Let me define it. Phase margin is a measure of how much the phase of the system lags behind minus 180 degree when the gain is unity, or we can say 0 decibel. The decibel part I'll come later in this lecture. First, let me explain what are these parameters: phase margin, gain margin. Is unity in the frequency response. Frequency response plot. The phase margin indicates the stability and robustness of the system. How we can interpret phase margin? Let me write interpretation. A large phase margin indicates better stability and robustness. Generally, they are positive in nature. Typically, a phase margin of 30° or more, basically positive values, more desirable for stability. And control design implication, control design implication. To increase phase margin in the system, phase margin adjustment to the controller or the system or system dynamics can be made. The lead or lag compensator are often employed to achieve the desired phase margin. We'll look all these parameters using the frequency response plot, and it will be very clear. So this is how we can define the phase margin in the system and how we can increase the phase margin by introducing the compensator to the system. We can increase the phase margin. Now, let me explain the gain margin. Gain margin. Gain margin is the amount by which the gain of the system can be increased before the system becomes unstable. Before the system This is also positive value in nature, and that we'll explain later. Interpretation of phase gain margin. A larger gain margin implies greater stability and robustness. A positive gain margin, a positive gain margin indicates stability. And control design implications. Control design implications. Increasing gain margin is crucial for robustness against uncertainties and disturbances. A controller such as PID controller can be tuned to enhance gain margin. So this is how we can explain the gain margin and phase margin in a control system and how they are very important for getting the DGR stability and robustness of the closed loop control system. Now let's go how we can come up with the gain margin and phase margin from the frequency plot. Let's consider the following figure. Let me draw the figure. This is the magnitude plot and this is phase plot. So here, let's assume this is magnitude of J naught J omega. The interesting thing from here is we'll plot the open loop control system, open loop transfer function, and we'll come up with the closed loop stability of the system. This is very beautiful thing from the frequency response. And let's assume this is the 0 dB line, 0 dB. And this is frequency line. And let's assume this is phase of the open loop transfer function, G naught of J omega. And let's assume this is 0 degree and this is plus 180-degree line. And we have, let's say, another line in between. And this is 90-degree line. And below 0 degree, we have minus 90-degree. And this is minus 180-degree line. What is 0 dB line? 0 dB line basically here we are, the plot is in logarithm scale. 0 dB basically we can say that 1 magnitude of the transfer function of the transfer is 1. So if you take the log, it is basically 0. So this is in logarithm scale. So that's why magnitude generally we measure in decibel. And here, let's assume we are having the magnitude plot something like this, and for example like this, and for this something like this, and the frequency or the angle plot something like this, something like example. Here, this is basically, I can say, this is the point where it crosses the 0 dB line. This is basically, we say, gain crossover frequency. Gain crossover frequency. And the phase angle of the open loop transfer function when it crosses minus 180-degree line, this point, this is called phase crossover frequency. So this is also, we can say this is also omega, because phase angle also we can write in terms of frequency. So here And the stability, the system will be stable from 0 dB2. This is very, very important. The stability margin generally we defined in this range 0 dB2 minus 180 degree. So this is basically, if the margin stays in between this, then system is stable. And how to find gain margin and phase margin? Let's look. As per the definition, the phase margin we generally define from the gain cost over frequency. So what we'll do is we'll draw a line. So we draw a line from the gain cost over frequency till minus 180 degree, and this is actually this value. This is actually phase margin, which is basically positive value here. This point actually omega p, phase cost over frequency. To find the gain margin, we'll start from the phase cost over frequency and we'll draw a straight line to 0 dB. So this part is basically, gain margin. So this is gain margin also positive value. And if the margins lies between 0 dB to minus 180 degree, so we can say the system is stable. And if the margins in between minus 180 degree to 0 dB, the margins are generally positive value. Another condition to come up with the positive gain margin and phase margin, the omega z should be less than omega p. So another condition, this is very important condition. This is how we can come up with the gain margin and phase margin from the frequency plot. Let's take an example how to find gain margin and phase margin from this response. Let's assume omega g be the crossover frequency at which the magnitude plot crosses 0 dB line. The phase angle at omega z is phi c. Let's assume the phase margin we can calculate. The phase margin we can calculate equal to 180 degree plus phi c. So if you take an example, assume omega z is 2 radian per second and phi c is found to be minus 135 degree, then phase margin you can calculate as per the formula what you have derived before, 180 degree plus phi c. So here 180 degree minus 135 degree, which is 45 degree. So this is how we can calculate the phase margin from the frequency response. Now let's look how we can find the gain margin. Okay. Let's assume omega p be the crossover frequency at which the phase plot crosses minus 180-degree line. Let at omega c the gain is minus capital M. Then the gain margin can be calculated as the gain margin. So it means omega c is the, or here actually we are right, we can write it as omega p as well. It's omega p instead of omega c. So the omega p, the gain margin, let's assume minus M. Then the gain margin we can calculate as Gm equal to minus gain at crossover frequency. It is omega p. Or we can write minus M, which is plus M. So if you take an example, let at omega c or omega p, the gain is minus 15 decibel, for example. Then gain margin we can write minus gain at omega c, omega p we can write, and from this we can write minus 15, which is 15 decibel. So this is how we can find the gain margin of the system. Now let's look why we use the magnitude in Bode plot or the frequency plot in dB. Let me write the heading. Why the magnitude in Bode or in frequency response? Because in Bode actually where we plot the magnitude and phase of the open loop transfer function, how they are varying with respect to frequency, and this plot actually we call the Bode plot. Okay, frequency response in dB. Let me write the note why you are using dB. The use of dB, decibel, simplifies the representation of the magnitude of a system transfer function over a wide range of frequencies. It means we can here basically every 10 times of frequency generally we measure. Suppose if you are starting from, suppose this is the 0 dB line, and you are starting from 0, 10, the frequency will vary 0, 10, 100, 1000 like that. So this is how we denote this dB. Over wide range of frequency, instead of 0, 1, 2, 3, just we are multiple of 10, and we can simplify the problem. And another advantage is in the dB scale, gains are additive. which simplifies calculations in the linear scale. In a linear scale, multiplication of gain components, I can write the gain correspond to addition of logarithmic values in dB. So basically what you do is, suppose we have transfer function g naught j omega, for example. So maybe it is j omega plus 3, j omega plus 4, and we have another term, the numerator, for example, j omega plus 8, j omega plus 10. So here what we'll do is, if we take the log of the transfer function of this transform, it will be some addition and multiplication. So if we take the d, basically we take the 20 log of both side, and we can come up with some simple form of addition of the different poles and zeros. So we'll take an example, then it will be clear. So let's take an example. Let's assume that g naught of is, for example, k into gp of s. So here k is the controller gain and gps is the plant. And if omega p be the H crossover frequency, then we can write g naught j omega, the magnitude k into gp j omega. And if you take the 20 log both side, 20 log g naught j omega, we can write 20 log k into gp at j omega. So this is, or we can write 20 log k plus 20 log gp j omega. So it was previously in multiplication form, now it is in addition. So we can easily visualize that individual component in the transfer function. So this is very quite easy to analyze the system. And if you would like to solve the magnitude at phase crossover frequency or at omega p, we can write 20 log k g naught j omega p. We can write 20 log k plus 20 log g naught j omega p. So this is how we can solve. And generally we find the gain margin of the system at omega p, phase crossover frequency. So if you'd like to find the gain margin for this particular transfer function, we can write gm equal to minus 20 log g naught j omega p. So, or we can write, we find gm minus 20 log gp j omega p, since, okay, now so here we are not taking this part, we are taking the this part only, because here omega p is not coming into picture. So in this part only we are getting the omega p, The transfer function we can write here, since the gain K does not change the phase crossover frequency when the gain K is adjusted. So this is how we can find the gain margin in log scale. Let's stop it here. In the next lecture, we'll be taking an example how we can design control algorithm using phase margin and gain margin in frequency domain, basically autopilot of the system. Thank you.